Okay, yeah, so you can see my slides, right?
Yes.
Okay, perfect. Yeah, so I'm Igor Sfiligoi. I'm here from UCSD San Diego Supercomputing Center. My title is a lofty lead scientific software development researcher. Essentially, I have been working with distributed high-throughput computing, grid computing for the longest time, both on-prem and in the cloud. And more recently, about 5 years ago, I started working with Kubernetes. But I have also been involved with HPC, MPA-based computing for more than 5 years now. So I see, I have been able to see both sides of the world. And I'm not a proper IT person. I rarely do any system administration, although I'm asked sometimes to help, but it's not my main role around here. I mostly work directly with science communities, and I have been working with a lot of them. The ones that I'm mostly active right now with astrophysics, computational biology, magnetic fusion, and high-end geophysics. But I have touched with many others too. So just to give an overview what my background is, and I try to convey what we have in this webinar through that lens. So as we said, we are talking about scientific computing with Kubernetes, and let's get this going. So before we go to Kubernetes proper, let me stress that most of what you have here, it's because of containers. We are definitely living in a containerized world. Containers are becoming the norm for a lot of science communities. There are many runtimes that can manage containers, but the whole idea of containers has become pretty mainstream by now. And why is that? Well, it helps with code portability. You just pack everything you need inside the container. You don't have to ask your system administrator to install libraries you need. You put everything you need inside the container and then running it like it was your machine. It's sort of related to a virtual machine, but a much more lightweight solution. And unlike virtual machines, containers themselves will typically contain code, may even contain input data and configuration, but they are stateless. So after the container goes away, you lose all the output unless you store it somewhere else. So that's something to keep in mind, and something that bites new users, but they usually learn pretty fast. Now, you can run containers on your laptop, and I know a lot of users do that when they do a small scale, but when you want to scale up, you end up needing running on different machines, and those machines need to run containers for many users. So you start need to manage many users on many machines, so you need something to coordinate that, and that's often called orchestration. And Kubernetes, here's a screenshot, advertises itself as a production-grade container orchestration. That's what it's good at. And we'll go over what makes Kubernetes good or even great at doing that. Now, first, what is Kubernetes and where it came from? It was originally created by Google because they run at scale. But they decided to open source it and contribute to an external organization, which is the Cloud Native Computing Foundation. And here is the link to where you can find everything you may possibly want to know about Kubernetes. I mentioned it open source. It has a very large and active development community, and I forgot to mention here, it has become a de facto industrial standard. So a lot of people use it, and it has a very active community. A nice thing about Kubernetes, it can be deployed anywhere. You could even deploy it on small scale on a laptop, but it's definitely available at HPC centers. For example, SDSC has a few systems that are Kubernetes based, but it's also available at all major clouds, Google, Amazon, Azure. And you just need to go there, provide your credit card, click a few links, and you get a Kubernetes cluster to play on your own. So this is not a hands-on webinar, so you will not be able to exercise anything I tell you here during this webinar, but you can go to any of the clouds, and for a few dollars, you can try out everything I told you here. So we said we are talking about containers, but Kubernetes really doesn't manage containers on their own. It really, the most basic thing you will do in Kubernetes, it's a pod. Oh, and I forgot to mention, it was the slides, that Kubernetes is also often shorthanded as KTS. So you'll see a lot of KTSs on the slides, but they always pronounce Kubernetes. So back to pods and containers. In Kubernetes, you really don't manage Kubernetes independently. You really manage pods, and a pod is just a set of container where a single pod, it's container in a pod is still okay, but doesn't need to be. You can have as many as you want in principle. And why is that? Well, because pods are what is scheduled in Kubernetes, and a pod is all the containers in a pod are guaranteed to run on a single node. So they can talk to each other, typically through the file system, but you can use networking too, and other fancy mechanisms. While different pods can be scheduled on different machines, so it's way harder to have any kind of coordination between containers in different pods. So if you want to have many containers talk to each other, definitely pack them together in a single pod, and that will make it much easier. Now, the focus of this webinar is trying to show you what Kubernetes can do compared to what batch systems can do. So the first thing you will encounter is that unlike batch systems where the system administrator will provide a bunch of software for you, to first approximation in Kubernetes, you have to bring your own software. So and that you do that by specifying a container image your job will run in. There is typically no defaults. Some Kubernetes administrators may do something to give you a default, but typically you don't. You specify the container with all the software you want when you create your pod, which think conceptually as a job in a batch system. And if your pod has multiple containers, each container can have a different image too. So you can mix and match. And sometimes that's convenient, although don't abuse it. It's easy to shoot yourself in the foot. Typically, images are externally hosted by default. They get from Docker Hub, but they can get from any other arbitrary URL. And your Kubernetes system may actually have an image repository that is collocated with the system. That's really dependent on the system administrator, but Docker Hub, it's a safe bet. Now, having an image that contains all the software is nice, and you could create an image for each job, but that's probably an overkill for many reasons. So what you typically do, you create an image or pick an image that somebody else has created that has all the software you need, and then you configure it to do what you actually want to do for your job. So to do that, you need to inject something in the image that will allow you to specify what exactly your job will have to do. And there are really three mechanisms in Kubernetes. There are config maps, secrets, and environment variables. And I'll go over the three of them separately now. So by far the most flexible are the config maps, which is essentially just a collection of files that you create, tell Kubernetes it exists, and once this config map exists, you can mount each and every file inside that config map at any arbitrary location inside your container. There's really no restriction where you want to run them. You can even set permissions for each and every one of them. Typically, you will map each and every file independently, but you can even mount them all inside a directory if that's more convenient. One note, although the name is config maps, you are not really limited to config file. You can have any arbitrary files, even main executable and libraries can be injected there too. Just don't abuse it. It's not a very scalable solution. Really, if you have anything big, it should be in the image, because that's handled much more effectively. But stuff like scripts, small helper scripts, startup scripts, are ideal to be shipped inside the config map. And you can even make them executable when you map them inside the config map, inside the container. A slightly related concept is secrets, and it's meant for some information that is more sensitive, like passwords and tokens. It provides slightly more protection than config maps. For example, you cannot really see from your laptop what the content of it's encoded. But once you and when it's mounted inside the container, Kubernetes makes sure it doesn't persist on disk in case of crashes and stuff like that. But that's about it. While the container is running, your application has access to it. So the protection is minimal, but it's still a good idea when you have something that you want to minimize the risk of being exposed. But conceptually, treat it like an advanced config map. And finally, the environment variables. Like with batch systems, you can inject config variables into your running environment inside the container. And they're the easiest to use because you don't have to create an independent object like with config maps or secrets. You just define them while you define your pod. And when you run, you see them. And they are often used in conjunction with config maps. So you have file-based configs that use config maps for the major things, but those are parameterized based on environment variables. So by combining the two, you get the best of both worlds. So that's for configuring your container, but as we all know, most application will need some storage too. It's not all in memory. So how do we deal with it? Let's first talk about ephemeral storage, which is what the terminology used in Kubernetes for the work area while the pod is running. All the areas in the container image itself are typically writable. The Kubernetes admin may disable it, so don't strictly rely on it. But to the first approximation, you can write anywhere in the file system without a problem. But it's typically small. You have a limited amount of free space, and it's relatively slow. So I would not recommend doing that for anything but small files and temporary files and stuff like that. When you need some more space, it's better to create a dedicated area that you will use as a scratch space. And you can do that by explicitly telling Kubernetes, I need an area called blah, 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 that will be my scratch space. And the concept for this in Kubernetes is called an empty dir volume. So you create an empty dir volume, you tell it how big it is. You can even tell it with what kind of storage you want if you have there are options, and then mount it wherever it's convenient for you. Typically it's this based, but it can be also based on the RAM disk. Of course, it will be much smaller because you are using extra RAM, but that's an option. And I mentioned that because while you will have the typical dev shared memory in all your containers, Kubernetes limits them to a very small amount, typically only 64 megabytes. So if you need dev shared memory, you actually need to remount it as a memory-based ephemeral storage in your container in order to get it as big as you need it to be. So something to keep in mind. I personally have been stung by that a couple of times. Now that's your work area, but you probably will have some outputs. So how do you deal with outputs? The ephemeral storage is just scratch space. The moment the pod goes away, it's gone. And when you start the pod, it's empty. what do you do with your data? Well, Kubernetes have many options, and there is really no standard. It depends a little bit on your system admin. But Kubernetes itself allows the system admins to provide many kinds of persistent storage. It can be a proper remote file system like NFS of Ceph. It can be in the form of block storage. So it's actually a block device. If you ever use the database, you know, they like it much better than a proper file system. The local storage itself on the nodes can be persistent, but be very careful when you use that because then you cannot move between nodes. And then there is any storage that is outside the pod itself, outside Kubernetes. Like S3, HTTP-based stuff, GitHub, Globus, SCP. They are not really managed by Kubernetes, but you will most likely use them one way or another. So I list them here because it's something you will have to think about. So after you decided that you need the storage, Kubernetes-managed storage, how do you make use of it? It's actually a two-step procedure. First, you need to pick where the data resides. And in a typical Kubernetes system, you will have many areas to pick from. It's really easy in Kubernetes for the system administrator to allow users to have their own areas that are completely independent of all the other users in the system. It may even be self-serve, but eventually you will end up with something called a persistent volume claim, which is the area you would want to use. And then you can mount it inside the container at any location you want. Again, no restrictions, and different pods can mount it at different locations during the lifetime of the persistent volume claim. So persistent volume claim will be there for as long as the data needs to leave, but each pod can potentially mount it in a different location. Not that I would recommend it, but it's an option. So that's the basics. Now we said you really want Kubernetes to manage many nodes and many pods, so you need somehow to schedule which pod we run where. And Kubernetes comes with a matchmaking scheduler, a little bit like you are used to in traditional batch systems. So each pod, so Kubernetes will match pod to available resources, typically CPU, memory, GPU, but can be even more complicated than that because each node advertises what is available, each pod specifies what it needs, and then Kubernetes will do the magic and find a place where the pod can run. The scheduling is not very fancy. If you are used to traditional batch systems, it's a little more than FIFO, but it's a priority FIFO. So you can actually specify that your pod it's less important and can go away in case a higher priority pod comes in. If you know how preemption works, yeah, it's essentially preemption. Can come handy in certain circumstances. Many of you may not need it, but it's good for you to know it's available. And that's pretty much it in terms of the basic concepts. I want to get a little farther now and talk about proper jobs in Kubernetes. So pods are the basic concepts in Kubernetes, but you can build on top of it. And a lot of things build on top of it. And bad jobs, it's one of those concepts. So a job is essentially a handler of pods that makes sure that your pods will actually run to completion. So if for whatever reason a pod is killed, if it's part of a job, the job will resubmit it, and it can even check the exit status and make sure, oh, it exited with a non-zero exit status. Let's try it again somewhere else. that's one reason why you want to use pods, jobs. And another one is that you can actually create a ensemble of jobs and launch the pods and run them as a single job. So you submit a single job that will run, let's say, 100 of pods, and you don't have to submit 100 independent ones. You just submit a single job that will make sure all 100 of those instances will run to completion. Think Monte Carlo, for example, generation, where you just want a bunch of independent jobs that run, and to get enough statistics, you can do it with a single command. So that's, I think it's something you really want to use once you are past basic toy pod examples. So that's all I have regarding concepts. We'll go a little bit in detail here on how you actually use Kubernetes. Again, unfortunately, this is not a hands-on webinar, so the detail is sort of limited, but I hope I provide you enough information for you to actually do try it out on your own on any Kubernetes cluster you have access to. So first, let's take this step. Unlike most batch systems, there are really no submit nodes in Kubernetes. They have this cloud native philosophy where any device can be used to control Kubernetes. And what you will usually do is you use your laptop. So your laptop is where you run everything. You don't need to SSH somewhere. You don't need to go to an external portal. You install just a local tool on your laptop and run everything there, which is really convenient. On the downside, this also means that there is no shared storage areas, because you can submit from one node and then monitor and fetch output from another one. So if you have 3 laptops, you can interchangeably use any one of those to control your jobs. So there is really no local stays on your laptop. Everything is managed by Kubernetes, which also means that you will have to explicitly move data between your submit node, which would be your laptop, and the Kubernetes system you're talking to, which is a little annoying and inconvenient, but that's how it is, and you will have to deal with it. So that's the concept. How do you do it in practice? In practice, while there are several ways to access Kubernetes, typically kubectl is the most used tool. It's a simple static binary, which is available for all major platforms. There's the link on how to install it. You just drop the static binary anywhere in your path, make it executable, and you're pretty much ready to go. Of course, you need to tell it which Kubernetes cluster you will talk to, because there are many providers of Kubernetes, so you need to tell him which one to use. And you just drop a config file in the right location, or provide that in the command line if you have many. But typically, users have access to one, and you just specify where it is, and you are ready to go. And at this point, this is what it looked like. You run kubectl with one of the commands you wanted to do, and do with it. So this is just a screenshot. Don't be scared. We'll go a little more in detail what those mean in the next couple of slides. But before we get there, it's really important to understand that when you use kubectl, you will deal with YAML as the job description language. So everything pretty much in Kubernetes is YAML based, at least by default. So you will need to learn how to read and write YAML before you can do anything regarding Kubernetes. Now, YAML is relatively easy to use because it was created with the aim of being a human-friendly markup language. We'll have some example in the next slides, and you'll see it's relatively easy to read, if not, and not too hard to write, as long as you learn the syntax. The one thing that is really important to understand is that it uses Python-like indentation to indicate nesting. If you don't have Python experience, you may be in for some pain. But anybody who used Python and understand that indentation is everything, well, yes, it's here. Is the same here. Make sure you properly indent everything and things will work. Else, it looks perfectly fine to a human, but it will really complain with weird error messages. So here is an example. So this is probably simpler than anything you will ever use in practice. And you see it barely fits on the screen. If you look at it, you'll probably see it's not hard to understand what it's all about. But yeah, it's very pedantic, very verbose, and there's not much you can do about it, unfortunately. So get used to it. After a while, it's actually, you appreciate the power of all that verbosity, but it can be a little annoying. So start from a template and build on top of it. That would be my recommendation. Now, don't worry about this. This is just an example. I will not go over it. Here is pretty much the simplest pod YAML that actually works. So this is a very simple pod that has all the bits and pieces you need to actually make it work. And let's go over the various things that you will need. So you'll probably start with the template, and here I'll showcase what you need to customize in order to get what you want it to be and not just being an example. So first, you must pick a unique name. Unlike most batch systems where you don't pick a name and you just get a number back and then deal with this number, Kubernetes expects you to pick a name. Now, I think one of the latest version of Kubernetes actually allows you to just set it auto-generated and then just get some garbage out that you have to memorize, which is equivalent to the job number. It is recommended that you actually generate the job name, the pod name on your own, and then use it. Other thing you will have to pick is the container image. Like I said, unless you have a very, let's say, weird Kubernetes configuration, there is no default. You need to pick the image you want to use. And finally, you have to pick the command you want to run. So as you see, you can essentially provide the command line separated by in pieces, and it will be executed inside this container. This is a simple sleeper pod, probably not the most useful, but it can be the base for an exercise. Once you have that YAML file, you just say kubectl create -f, the name of the YAML file, and boom, the pod will be created for you. Now, you want to see that the pod is actually there. So how do you do that? Well, kubectl get pods. It's what shows all the pods that have been ever submitted to kubectl, to Kubernetes. And it gives you just a nice listing. If you want to know more details, you can use the -o wide. That's my recommendation. It gives you a little more detail than just the default, but it's up to you. It will tell you if when you submit a pod, it will just send initially, well, it's there, it's pending, which means it has been submitted, but it's not running yet. Hopefully, it will start to running fast. So by the time you run kubectl get pods, it may already say running, which is great, but sometimes that doesn't happen. So you need to know how to actually check why it's not running. And kubectl get events is your friend. It tells you what Kubernetes is doing about your pod. Unfortunately, the ordering of these events it's very inconvenient. So you will probably want it to be in chronological order and that's not the default, unfortunately. So you will need this long argument to tell it, please list them in chronological order with the most recent one last. And that will make it much more readable. And finally, you can also, once the pod is running, you can actually log into it, run any arbitrary command, which is great for debugging. Or you can even submit a sleeper pod like I did in the example before, and just run a bash shell in it, and it becomes a complete interactive node. So by combining a sleeper pod with kubectl exec, you can actually create your own interactive pod to use inside Kubernetes, which is great for prototyping. Don't use it at scale. You are wasting resources because it's just a sleeper pod, but it's great for prototyping. So if we put it all together, let's create the sleeper pod with the YAML like we did before. You create it, then you'll start checking if the pod is running. Hopefully it will start soon. Once it's running, you can essentially log into that node. This is effectively a login into that pod. It should be pod, not node, but okay. You're not on the node at the host level, you are inside the pod. And remember to delete your pod at the end. Kubernetes will pretty much keep the pod around forever, or a very long time at the very least. So you get a lot of garbage if you don't clean after yourself. So you are expected to explicitly delete your pod after you are done with it. Now, that was a very simple interactive pod. As I said, you probably want to do something a little more fancy. You want to configure it somehow. And here is an example of a config map. I'm creating a config map with 2 files in it. And then when I submit my pod, I tell it, please, from my config map that I called myconfig, get the file p.py, and then mount it at this location, opt code ppy. Oops, sorry. And then you need to, so we are matching the name here, we are matching the name here, we're matching the names here. So you see it's very verbose, but apart from that, it's not too hard to follow what it's doing. And after you've done this, when you launch, when the pod starts to run, that file is available, and we can use it as part of our command line. So this is a simple example how to run your custom startup script using Kubernetes. As I said before, don't abuse of the config map. They are not very scalable. Keep small files in there and put any big stuff in the image itself. But for simple scripts that are a few kilobytes in size, this is probably the easiest and most convenient for most users. And you can use any stock image that's available in GitHub. Here is a slightly more complicated example where we also inject an invariable environment variable into the container, and this my code py. Here I assume that we'll read this environment variable and do something about it. Just a simple example, nothing fancy, but it exercises a couple different things. You are getting a file from a config file, mount it, run it, and then this file actually uses a an environment variable that we injected at runtime. And here is an example of more storage. So in the previous example, we really have no storage. hopefully this is printing something in the standard output because we are not storing any other thing anywhere. In this case, we actually are telling our pod to go and use a persistent volume claim called example volume, which hopefully exists, and mount it at the location /data. And in this example, I'm assuming this data has been already populated. This persistent volume claim already had some data in it. In particular, it has an executable and some data. So this pod will just use them and probably write something back to it. It's an assumption here. Hopefully it will work. If the data is not there, obviously everything will fail. But assuming you know what you're doing, that's a nice way to set up your working environment and just work out of them. And this brings us, well, okay, nice. How do we get whatever we have computed out of Kubernetes? Well, the easiest is just fetching the standard out and standard error out of the pod. And you can, for that, you just use kubectl logs and the pod name. And in the case of our P example, hopefully it has printed something out, and we just run kubectl logs and see what that was. If you have used persistent storage, well, it's there. You can use it. It will not go away. It will stay there for as long as the persistent volume claim exists, which means nobody has deleted it, which it will nobody should unless there is a good reason for. The problem is just how to get it out. Well, Kubernetes by itself doesn't really help you there. You will need your favorite non-Kubernetes tool to do it. And it really depends if there is another way to access that persistent volume claim through, I don't know, S3 or Globus. If not, you just essentially start the sleeper Kubernetes pod and use SCP to copy it back and forth. So here is how we put it all together. For example, for the P example, you create it like before, wait for it to start. Anytime you can fetch the standard output, standard error. Definitely you can do it at the end, but you can do it also while the pod is running. So at any point in time to tell you what the standard output, the standard error is there. And when you don't need it anymore, delete it. Just remember, after you delete it, there's no way to call kubectl logs. So all standard output and error is lost. Unlike most batch system, which deliver that file back to your submit node, there is no submit node here. So it's your responsibility to fetch any standard output and error before the pod is deleted. Let's now move on to something a little more advanced, which is the requirements. So here we have an example where we are asking for one CPU, one GPU, and some memory, which is similar to what we had before, but we don't want just any GPUs. We actually want to be a little more fancy, and we say we only want the latest Ampere-based ones. Now, when you do that, you restrict yourself to only those. So if those are not available or not available right now, you will wait until those are available. The good thing is you will get exactly what you asked, but the downside is that you will have to potentially wait longer. Now, if those are not hard requirements, you can be a little more flexible. In this case, we are still asking for one GPU, but we say, look, I really don't want older GPUs like the 1070 and the M40 that I know are in the Kubernetes cluster. I really would not like to use them. But look, if this is the only thing we have, I'll take it. So this will not delay your startup times, but you may end up with those GPUs, although if there is anything better available, you will get it. And finally, a word about limits. As I said, the requests are what is used for scheduling, and you are guaranteed to get that. But as we all know, compute is not always homogeneous. You often have spikes in both CPU and memory usage. So you can put the limits slightly higher than the requests. They're not used during scheduling, so they're not guaranteed to be there all the time, but they likely will be because others have a similar behavior. So in this case, we ask for 1 CPU, but allow up to 2, and we request for 12 gigabytes, but we allow to go up to 16. In the case of CPUs, Kubernetes will just throttle you if you try to use more than 2. For the memory, it is a little more strict. If you exceed the 16 gigabyte, it will be hard killed. Is try to stay under 12, but if you exceed it a little bit, it's still okay, but you want to be killed if your program is misbehaving and exceeding 16 gigabytes. So that's one of the advanced features you get in Kubernetes. Once you have put that into a YAML, the submission is all the same, so nothing is changed, everything is in the backend. Let's spend a word or two on jobs. As I mentioned before, you want to do them because they have several benefits. As you can see, it's very similar to what we had before. The header is slightly different. The bottom part is pretty much the same, but you have this middle part where you actually tell it job-specific things. And in this case, we're actually asking for 10 pods to be submitted with a single job. And we also ask it to be indexed, so we get an index environment variable you can use in your job. For example, if you do a Monte Carlo and you want 10 executions, you can use that as your seed number. In the submission, again, it's very similar, but you must understand that jobs, objects, and pod objects are completely independent. So if in order to see your jobs, you actually have to use kubectl get jobs. Now, jobs is with pods on your behalf. So in order to monitor the pods themselves, you still use what you have done before, kubectl get pods, and you can get the logs from kubectl logs like you did before on the pods, not on the jobs. But just remember the two are independent. So when you deal with jobs, remember you're doing it with two objects. Yeah, you submit the same thing, but then you have to do both get jobs and get pods, and logs go on the jobs themselves. And remember to delete the job in the end. So that's all I have for pure Kubernetes. Let me now go over a few advanced topics. First of all, I would like to make you consider what you do when you have something that is more than a simple bad job. You can use Kubernetes directly. We saw it before. You may need a little bit scripting, for example, for name handling and I/O. But in general, for simple jobs, it's easy. When you have something more complex, you have Helm that can help you. It has become the standard for Kubernetes deployments. And there are most of the major software providers have their packages packaged with Helm, and there is even a website that lists them all. So I encourage you to look there. Since we are all in HPC land, what about MPI jobs? You may have noticed that there was no MPI so far. Well, the truth is Kubernetes does not normally support MPI jobs out of the box, but you have external projects that can help you getting a cluster to support them. For example, in Voyager, here at SDSC, we use Kubeflow, and there is a link there. Moreover, usually Kubernetes schedules one node at a time. So multi-node scheduling or GAN scheduling is typically not supported out of the box, but there are external scheduling plugins that can be used and can be helpful there too. Not going to details, you can read it up at those links. Another thing that may be useful when you want to go a little more adventurous, it's networking. Unlike traditional batch systems, networking is a first-class concept in Kubernetes, and each pod, actually each container in each pod gets its private IP address. So it makes it easy to talk between containers using the networking. The only problem is that the IP is typically non-deterministic, so you need to find a way to exchange what that IP actually is. To help with that, you can create a service object that has a permanent network address, both an IP and a cluster local DNS entry. And it can be used to route the traffic to those pods, typically in round-robin fashion. Again, not going in details about it. There's a link, but be aware of it if you want to go beyond pure batch computing. As with most batch systems, you typically have no incoming networking from the WAN. You have typically only outgoing connectivity, but kubectl has a nice port forward option that is similar to what SSH allows you with tunneling. So, for example, you can start your Jupyter notebook inside a pod, establish a tunnel with kubectl port forward, and then attach to the web instance of the Jupyter container in a very easy way from your laptop or desktop or whatever you're using. For more wide deployments, there are also more complex things like ingress, where you can have public DNS entry that will route the HTTP traffic to the pods in the backend. You need some help with admins typically to do that, but it's powerful if you want to host web servers in Kubernetes, for example. And finally, I would like to stress that while Kubernetes is very powerful by itself, it's really the surrounding ecosystem that makes it so valuable. Personally, Kubernetes is okay, but by itself, it's not something I would really recommend. It's really useful, though, because there is so much support around it. It has become a de facto industry standard. There are many projects that built on top of it to deliver additional capabilities, and help and MP extensions that I mentioned are just the tip of the iceberg. So I would really encourage you to explore it, because there is a lot that can be done with the Kubernetes being the backend, and that's, I think, its major benefit. But if I haven't sold you on direct Kubernetes access by itself, I would like to point out that Kubernetes resources can be easily used through an overlay system. For example, we have done this in OSG through HTCondor. So somebody can create an HTCondor overlay system on top of Kubernetes resources, and users only see HTCondor and never see Kubernetes and be none the wiser of it. Of course, you lose some of the flexibility of pure Kubernetes, but if all you do is batch computing, that works as well. And that's all I have. I hope you enjoyed this webinar and have learned a lot. Thank you.